Hello everyone, and welcome to the 58th session of the Porous Media Tea Time Talks. We are part of the Interpol Young Academy, and with this platform, we aim to bring early career researchers, PhD and postdocs, the opportunity to present their research to our worldwide porous media community. So I'm Sarah, I'm now postdoc at Geological University. And today in the studio, I'm joined by Sankti from the University of Minnesota and Negar Nazari from the CNRS in France. So today we have a late session because we have two speakers from different areas, one from Europe and one from the US. So without further delay, I will introduce our first speaker, Riccardo Sprocati, who is a postdoc at Technical University of Denmark, and he is working on the project EKRAM, electrokinetic way to green remediation technologies. And he focuses on numerical model development for process-based and surrogate simulators. In previous project, he worked on electrokinetics technologies for both remediation applications and metal mining, life cycle assessments, data analysis of large environmental datasets, software development for reactive transport motors, and high-performance computing applications. And today he is going to present his work on enhancing solute transport in porous media with electrokinetics. So, Riccardo, thanks for joining us today in the platform, and the floor is yours.
Thank you, Sarah, for the introduction. So what I would like to discuss today is ways in which we can enhance solute transport in porous media with electrokinetics, and especially in heterogeneous porous media. But let's start with a general outline of the presentation. So I divided it in two parts, which in the first part I would like to give a very brief overview of conventional groundwater transport, the issues faced into the remediation. And then I will move on talking about the principles of electrokinetics, what it is, a couple of equations, and especially what are the main applications. And in the second part, I would like to show you the results of some laboratory experiments that we did at DTU, and also some model-based interpretations. This will especially focus on the role and interplay of electromigration and electroosmosis in heterogeneous porous media. So let's take a look at this very simple example of a homogeneous porous media. So we are in an aquifer, and we know that if everything is homogeneous, the flow will be homogeneous, the streamlines will be simple, and the overall solute transport is very predictable. But what happens in reality is that you have heterogeneities, and this can be because of different grain size distributions, can be different materials such as sandy layers and clay layers. There can be any different sizes and forms, and what they do when we talk about the groundwater transport, they create preferential pathways. And if we consider a contaminated site in which a contaminant has been there for a long time, I can say years or even decades sometimes, the contaminant, even if could not penetrate into these low permeability inclusions because of advection dispersion, just by diffusion, it could enter these low permeability inclusions. And when it's time to perform remediation, you can do pump and treat, in which you actually pump water out of the system. And that is effective into removing the contaminants from the higher conductivity parts of the aquifer. But the bottleneck of this system is the mass transfer limitations, because this contaminant that has been trapped into these low permeability inclusions takes quite a long time to back diffuse out, and this has two main consequences. The first one is that you might have to pump for a very long time before taking out all the contaminant from the low permeability inclusions. And the second one is that if you stop pumping at some point, you might have that after some years you go there, you do measurements of the water quality on the site, you found out that the contamination went up again. And this is because you didn't remove all the contaminants from these local meeting rooms. So to overcome and to be able to provide a way to remove and deliver solutes into low permeability matrices, such as clay, for instance, which are very common. From the 90s, there was this class of techniques called electrokinetics that have been developed. The idea is that you can use electric fields directly in the porous media to enhance the transport. So in the field, this is done essentially by putting electrodes into boreholes and applying a direct current. When you apply a direct current, the electrodes have a polarity and you have electrostatic effects. The main one is called electromigration. And if you just take a look at the Max-Planck equation on the left, you see that the total flux of the species I is not only due by diffusion, dispersion, or advection, but when you apply an electric potential gradient, there is also another term in red that is called electromigration. And that is because when you have electrodes of different polarities, the ions, they have a charge, so they move towards the electrode of opposite polarity. But not only the ions in the free water move, also the solid surfaces, they have a charge, and in natural soils at near neutral pH, the charge of soils is negative. So around the solid particles, there is a layer called diffuse double layer, or EDL, that has an excess of cations. Now, I will not go into the details of that, but when you apply an electric field, also this excess of cations move. And in this case, you have a movement of this mass of cations towards the cathodes. And if you take a look at the continuum scale, this results in electrosmosis. And that actually has the same effect as a water flux. And essentially, this contributes to the hydraulic pore water velocity. So the main applications of electrokinetics, or the one that have been studied the most, for instance, is the one in which electrokinetics is used for the remediation of contaminated sites. In my research at DTU, we did several experiments and investigations about it. One, for instance, involved the electrokinetic barrier remediation, chlorinated things, in which electrokinetics was used to deliver an electron donor, lactate, which is negatively charged, was delivered by electromigration, but at the same time we used electrosmosis to mobilize the organic contaminants, in this case chlorinated things, so PC, TC, and so on, and provide bacteria delivered by electrosmosis. And we did process-based investigations, and also this has been done in the field. It is quite effective. Then another application, a recent one of electrokinetics, is for in situ recovery of critical minerals, in which you use specialized chemicals, lixiviants, to dissolve the minerals present in the subsurface. They dissolve these metals, they go into charged form, so copper ions, gold, and so on, and then you can recover them. And this way you can overcome the physical limitations posed by conventional in situ recovery. And this has been proved for intact rocks and tailings. But the research question actually is, all these studies have been done for homogeneous porous media. And what we wanted to do, and we asked ourselves, is can we use really electrokinetics to enhance solute transports in heterogeneous porous media? And then the natural question is, what is the interplay between electromigration and electrosmosis in heterogeneous porous media? So we did that with different experiments and models in an article published a couple of years ago, in which we used this setup, very simple. Just to give you a scale, is about 60 centimeters wide, and here there are three parts. At the sides, there are electrolyte reservoirs in which there is electrolyte. So, for instance, a buffer, the simple bicarbonate buffer. Then you put electrodes, and in the central part, there is the porous media. Here we use two different types of glass beads with different diameter because we wanted to provide let's say, a domain, and then we created an inclusion. And that was representative for us of heterogeneity. We used glass beads because it's a relatively simple porous media to work with, but also we wanted to understand as much as the processes that were going on without any complicating factors. And here the experiment was to investigate the transport of a Lua red, a charged tracer with charge -2, and the transport and the interactions with the inclusion that you see in the middle as a response with the response of the electric field. So the first experiment that we did, we used a finer inclusion in a coarser domain, and the difference in electrical conductivity between the two domains is about 2 orders of magnitude. We used a pH of 9, so quite a high pH, and you see that the Lua red, the tracer, kind of goes around the inclusion. It is also what happens when you use just a advection dispersion with this porous media. But if you just change the pH, so you decrease the pH, you go to 2.5, the surface charge changes in the glass beads, and the electroosmotic flow, we could see that is almost completely reduced. And in this case, Lua red does something incredible. It penetrates almost completely the inclusion. And the overall effect is that if you just take a look at the total pore water velocity here, in the first case is that you have that the domain, actually the inclusion, acts almost like a pump. So you have an advective velocity pushing against, so from right to left, pushing outside the Lua red from the inclusion. Whereas in the right side, when you have a low pH, the electroosmotic flow is reduced. So this kind of pumping effect of the inclusion is almost completely neglected, completely eliminated. And another important thing that we could prove with this work is that electromigration is not dependent on geological conductivity, but is dependent on the tortuosity. And we could demonstrate that even if that tortuosity is not dependent on the grain size, but as you see from the 2.5, the pH 2.5, the experiment can overcome this physical limitation. Then using models, we could identify different patterns, and we can explain the different transport mechanisms, and just to provide an indicator with this matrix, we can identify in the domain which transport mechanism is dominant. And for instance, the red color means that in the largest part of the domain, electromigration is the main dominant mechanism, whereas the green color indicates that there is an equilibrium between electromigration and the advective velocity. And this is why you don't see a Lua red entering the domain. Whereas when the pH is lower, the electroosmotic flow is lower, and most of the domain is affected by electromigration. Then another interesting experiment that we did was in the same setup as before, but instead of a Lua red, which is a non-reactive tracer, we used a reactive one. We used potassium permanganate. And still using a low permeability inclusion, we also put glucose just in the inclusion, and glucose reacts with potassium permanganate. Here we did 3 experiments, one with advection and 2 with decay. In the one with advection, we moved the potassium permanganate from left to right. And as expected, potassium permanganate just goes around the low permeability inclusion. And since we cannot visualize glucose from the images, we used a process-based model to visualize if the plume of glucose has moved. And as expected, it didn't move that much because the hydraulic velocity inside the low permeability inclusion is very small. But in case of electrokinetics, even with a high pH, also in this case, as was with the Lua red, we didn't see the permanganate entering the low permeability inclusion. But actually here it already reacted with glucose, because glucose is not charged, but it has been pushed out completely and very quickly from the inclusion. And that mixed with permanganate and reacted outside the inclusion on the left side. Whereas in the case with lower pH, we could deliver permanganate all throughout the inclusion. And in this case, the mixing with glucose was actually throughout the potential permanganate plume. So another important point is that you cannot only engineer the delivery of a solute in electrokinetics, but also the mixing dynamics are quite different, just by changing the solute composition. So to conclude this work, just want to summarize the main points that I think are interesting. That in this work, we could identify that there is a strong interplay between electromigration, electrosmosis, and electrolyte transport during electrokinetics. And this has a very, very important impact in the heterogeneous transport. But also, here I just show you one case. In the paper, there are some others. We can take advantage of that interplay to really engineer and target different electrokinetic applications to deliver and mobilize both charged and non-charged species in low permeability zones. And that can be done at a higher speed with what is possible to do with just advective diffusive transport. But also, not only the transport is different, also the mixing dynamics are different, because with electromigration, you move cations from one direction and ions in the other direction. And then if you have non-charged species, they can either remain immobile and you have, for instance, the cations going through them. So also the mixing with electrokinetics is much, much higher with respect to advection, dispersion alone. And we quantified in a paper that is order of magnitude higher. And lastly, I didn't focus so much in this work, in this presentation, sorry, but with a lot of work with process-based models, and these really are very, very useful tools to identify the main processes that are going on, because you are able to identify the different contributors. So when the complexity is higher, models are really useful to disentangle this complexity. So thank you so much for this opportunity, and I'm looking forward for your questions.
All right. Thank you, Riccardo, for a wonderful presentation. It was really enjoyable and very technical. I really enjoyed the talk. And now it's time for a Q&A. So those of you who are on YouTube watching this, if you have any questions, please type your questions on the chat. And while you are writing the question, I have a few questions to ask you, Riccardo. So I had two questions. One was, in the beginning, you mentioned about applying this in the organic contaminants, chlorinated ethyns. And maybe I missed, but you mentioned about enhancing transport of bacteria because the surface of bacteria are negatively charged. Can you explain more on how this technology can be used in bioremediating oil contaminants?
For oil contaminants, you can either directly mobilize the oil matrix, actually, because by using electrosmotic flow, you create really a water flow. So you can either move the oil directly, or what we found is that bacteria can be moved with the electrosmotic flow, so with the water flow. Then we also have another study going on in which we investigate the electrophoretic mobility of bacteria, and especially if we can engineer the surface charge of bacteria to move them more effectively with electrokinetics. And that has been showing some very interesting results.
Oh, interesting. And another question is about the practicality of the technology. I'm not familiar with this technology, so when you're imagining the real application of these electrodes on subsurface, how far can they be separated? I know it should be dependent on maybe the voltage applied, but what will be the practical distance or minimum distance or maximum distance between the electrodes in practical setting?
It depends on many factors. Just an order of magnitude, I would say from 5 to 40 meters. This is what we are looking at. We're not talking about the hundreds of meters.
I see. That's quite far.
There are different ways to engineer the technology. Yeah.
I see. We don't have questions yet from the YouTube. Was there any question from the members of the Porous Media, TTT, or? Yes, there's a question came up from Susmit. Thank you for the insightful talk. How did you ensure mass conversion of species while using complex coefficients in advection dispersion equations? Thank you.
I didn't show it in the equations, but actually you also need to consider the Poisson equation that actually regulates the charge neutrality among the species, because of course you move cations and anions, but they have different aqueous diffusion coefficients, so they move at different velocities. And you always need to comply with charge balance, right? So what we do is also we add another equation, the Poisson equation, and that regulates everything. At the continuum scale, what happens is actually that, when you are just in advection dispersion, as you move through the flow, the concentration just can decrease, right, because of mixing. In electrokinetics, the concentration not only can decrease a lot, but can also increase. So for instance, if you, and we proved it in a few papers, if you deliver an excipient or a tracer in a solution that has a much higher ionic strength, actually that increases. So you see that the plume shrinks and increases in concentration, and then it moves. And that is due because of this very complex interplay between concentrations, aqueous diffusion coefficients, current, conductivities, and so on. But that's a very interesting field of study, actually.
Okay, I don't think we have additional questions at this point. So let's thank our speaker again. Thank you, Riccardo.
Thank you so much.
Yes, and we can move on to our second speaker of this session, who is Dr. Negar Nazari. Negar is a postdoctoral fellow at the School of Engineering and Applied Sciences at Harvard University. Prior to her postdocs, she completed her PhD at the Energy Science and Engineering Department at Stanford University. Negar received a Trailblazing Research Award from the California Institute of Technology for exceptional contributions and frontier research in energy and sustainability. The title of her talk today is Geological Hydrogen Production in Basalt in Response to Hydrothermal Reactions. Negar, floor is yours.
Thank you, Sang, for the introduction. Do you see my presentation?
We see your screen. Can you share the PowerPoint slide?
I don't know what happened.
You can, in the bottom menu, you can hit the button that says present and then share screen. And then you can select the window, which will be your PowerPoint file.
Yes, that's what I did.
Oh, are you using two monitors, multiple monitors? That could be a reason.
Yes, and unfortunately I'm using Mac, so maybe that's part of the issue. Okay. How about now?
think it's shared. What you can also do is you can email us your PowerPoint slides, then we can try sharing it for you.
Yeah, I can do that.
So use mainly my email address if you want.
Yes, I do
You
that.
should have it.
Do you see it now?
So now we see your screen, so you can move to your presentation. Yes.
I think you
Okay.
can make it a full screen presentation mode, then I think we'll see your slides. Yeah.
All right, sounds good. And just hit the hide button on the bottom of your screen, please. Yeah. Sure.
I'm sorry, what happened? Okay. Can we move on?
Yes, sure. You can go on.
Can we move on?
Yeah, sure. Can you hear us, Negar?
Yeah. Okay. Hi, everyone. Hopefully you hear me. Today I am talking about the geological hydrogen production in basalt in response to hydrothermal reactions. So actually, for the many years, the climate and energy challenges are one of the main challenges for our generation. At the same time, we have the population increase in millions in many areas on the world. And the interesting point is that the increase in the population is happening in the areas that already have energy and climate crises. So it meaning that a lot of the people in those areas already do not have access to any electricity. So by increasing the population using fossil fuels or more types of energies, all of these challenges will be more pronounced. At the same time, we need to stick to a limit for the carbon dioxide emission into the atmosphere. So we need to take care of the resources that we are producing our energies from. There are multiple pathways for energy decarbonization. Actually, I put them in 5 categories. It starts from like energy efficiency, that is changing the building, vehicles, and appliances to be more energy friendly or environmental friendly by converting the energy using like the resources and the vehicles that are like consuming less, changing in the land use, afforestation, and improve grazing management. And the most two important ones are the fuel switching and the carbon capture and storage. The one that I'm talking about today is the fuel switching, and actually it's the energy production from hydrogen, which is a very promising area. The slide shows the hydrogen generation, the value chain. The figure in the right that shows the possible pathways that actually generate hydrogen from various energy resources, how hydrogen can be stored, and how it can be utilized. Producing hydrogen from natural gas using steam methane reforming is actually currently the most common method and the most economical method that is used to produce hydrogen. It accounts for 80% of the hydrogen production in the US domestically, and 47% of hydrogen production globally. The problem with the SMR, however, is that it emits a lot of CO2, and the rate of CO2 emission is 9.7 kilogram of CO2 per kilogram of hydrogen. That is a lot of hydrogen. And so that is a lot of CO2 to be produced. Considering all of these limitations, one of the promising areas and the promising resources that actually came to the play in the recent year is how to produce natural hydrogen. But where does actually natural or geological hydrogen come from? It can produce from 4 different sources. Sometimes people mix the first two and they just call it serpentinization under one category. The first one, the most important one, and the main process is called the serpentinization. Serpentinization is actually the metamorphosis of the mantle rock. The rock that actually contains a lot of iron, magnesium, silicates such as olivine, pyroxene, in ultramafic rock react with the water, and then it produces hydrogen. Hydrogen is one of the byproducts of this reaction. In the mineral oxidation part is the transformation of the reduced iron, iron 2 to iron 3. It changes from olivine to the oxidized iron that is actually found in the magnetite, and one of the byproducts of the reaction is also hydrogen. The third one is the radiolysis of water, actually naturally occurring element that decay the radioactivity, such as uranium, thorium, and potassium. The radioactive energy can break water when water actually hits them, and then they can produce hydrogen. And the last one is the deep earth source, the hydrogen that is coming from mantle, core, and can be produced through fractures and fault. That area is very unknown. The serpentinization, which is considered a very important source for producing hydrogen, is actually, there are some specific rocks or minerals that can produce hydrogen. Olivine is the first one. Olivine is a mixture of magnesium and iron. The magnesium part is actually forsterite, that is a magnesium silica, and the iron part is fayalite. The important part and the interesting part that we are interested in is the fayalite. Under reducing condition, the fayalite interacts and reacts with water, and it produces hydrogen. The maximum production rate that happens is under the temperatures of 200 to 350 degrees C, with the fluid unsaturated in the carbonate. So we need 3 conditions for that. We need to have the reducing environment, we need to have the high temperature, and we need to have the undersaturated fluids in the carbonate. The second one, which is not as popular as olivine, is called pyroxene. The only difference is that in addition to magnesium and iron, pyroxene contains calcium as well. And this one also contributes to hydrogen production through serpentinization. Other one is the iron titanium oxide and the sulfides. So where do we find olivine? Actually, the plot shows the of the igneous rock all the way from felsic to the ultramafic. We see that in the left side, in the felsic part, we have granite. The granite, it contains a lot of quartz, feldspar, albite, and some mica. But when we go to the right of the plot, and by increasing the temperature, we see that in the mafic and ultramafic region, we run into pyroxene and olivine. Those are the ones that have the potential. So we need to focus on those rocks, on those minerals, and the most important rock that contains actually olivine is called the peridotite. Peridotite is found enormously in the mantle, and in the areas that we can have access to the mantle, we can produce that. So in the ocean-rich areas and any area that the crust is actually thin, that would make it very easy to reach to that areas and to produce the hydrogen from them. The good thing about them is that they are available anywhere on the planet. It's just a matter of like how easy we can access to them. So the abundancy and the availability, maybe it's one of the factors that makes it really popular. In order to check these hydrothermal reactions and how they work, we actually conducted some experiments in the lab. So in our experiments, we looked at different samples of basalt, and we put them under hydrothermal, under high temperature condition in reaction with different water compositions. The temperature, we increased it to 250 C. The solution that we are reacting the rock with are DI water and brine solution. One of them that I'm showing today is the 33,000 ppm NaCl brine that is actually equivalent of the seawater salinity. And we add around 20 milliliter of the water to a core that is placed in a vessel, in a high pressure vessel. And we let it stay in the oven for 10 days. I need to note that at 20 degrees and 250 degrees C, the saturation pressure of water is around 40 atmosphere. In that condition, like 40 atmosphere and 250 C, water is still in the liquid form, so it's able to react with the surface of the rock. The sample size is 1/2 inch diameter and around 1/2 to 1 centimeter height. So a little bit about the mineralogy of the samples and the minerals that present there. We use 2 different samples. The first one is the Hecla basalt and the second one is the Antrim basalt. What is different about them is Hecla basalt is considered like a fresh basalt. A lot of the pores are still open. They didn't go under any tertiary reactions, and we have a lot of open spaces within them. However, in the Antrim basalt, they age around 50 to 60 million years. A lot of their porosity is a lot of the porosity within them undergone like tertiary reactions and depositions. So a lot of them are filled with tertiary minerals. But no matter what, the main composition in both of them is magnesium, aluminium, silica, iron, and sodium, and some traces of titanium. So when we reacted the samples with the water, we checked the composition of the water after 10 days. We saw a very huge increase in the pH of the solution. The pH of the solution that we started with for both the DI water and the brine solution, the initial pH was less than 6. Which is pretty normal for the DI water or the water that is in contact with the CO2 in the air. So, but after 10 days, we measured the pH again, and we observed that the pH actually increased to be around 10, and we created a very strong alkaline environment. So we wanted to look at the elemental elements inside the sample and see what changes we can observe. What we do is we put our sample under SEM, under confocal microscopy, NMR, and EDS, and then we try to understand all the changes, especially all the geological and mineralogical changes that happen in the composition of the rocks. You see from the top to the bottom, which is like before and after, one of the reactions that we did, the spectrum analysis in the right show a very strong difference from in all the elements from the top to the bottom. And also, just to be more accurate, we we try to extract the compositional element, the composition for each element across the surface that we are working with, and then we analyze those using the codes that which we actually generated for this purpose. So when we measure them, and actually in terms of number, so we observe that we see a decrease in the iron, aluminium, calcium, magnesium, potassium, and titanium. It means that we have a lot of dissolution of the primary mineral, which is the first possible reaction and alteration that happens during serpentinization. The other thing that we observe is the core by itself. When we looked at the sample, which is shown in the right bottom of the screen, we saw that initially it was like very dark black and clean, but after 10 days, when we looked at the sample again, we saw a lot of white precipitate on all the cores area, all the pores surfaces across the entire sample. So we checked that. We believe that we have the formation and the precipitation of the secondary minerals that could be like carbonates or any kind of silica precipitate that happens. Another possibility was if it is like clay or zeolite, but we cannot confirm if it's clay because we had a lot of silica and we see some silica precipitation in some spots in the left figure. We believe that can be some amorphous like SiO2. So then we wanted to see if we can actually quantify any of those changes that happens in the surface of the basalt. So we put the surfaces under the confocal microscopy and confocal imaging. The interesting thing is that we did not expect the confocal imaging to be useful because it's a rock surface. We don't have a transparent surface, and we were not that optimistic. But when we checked the surfaces on the exact same locations, the one in the left shows the samples in the DI water before and after the reaction, and the one in the right shows the before and after in the high salinity brine solution. So we observed that, interestingly, in both of the sample, the area percentage of the pores. We only talk about the surface. The reaction time was very short. The rocks are tight, so we cannot confirm if that changes in the pore volume actually happened across like the entire volume of the sample. But what we saw is that at least on the surface, we saw a lot of increase in the area percentage of the pores in both of the samples. Another interesting thing that we ran into is the formation of the dendritic structures that actually occurred on the samples. So we tested one of the samples and we opened the chamber immediately. We didn't let it cool down. Of course, we depressurized it. But when we scanned the sample right after opening the chamber without letting it cool down, we saw a very interesting dendritic structures on the sample. And we thought maybe it's by accident or random, but the same structure appeared on the entire surface of the sample. So we think that those can be some indication of the hydrothermal reaction that happened in the surface. I do not have any explanation for that. It's just interesting. I never ran into it anywhere. So we are still working on understanding that. But in 2 weeks, when we went back to the same samples and looked at them, we observed that those dendritic structures are gone and we don't see them on the surface anymore. So in summary, actually, we showed that the serpentinization transforms the ultramafic rocks into serpentine, magnetite, and hydrogen gas. We didn't prove the presence of the hydrogen gas, but we proved the changes that happens across the mineral in terms of the minerals on the surface of the sample. The reaction happens as soon as few days, which is very interesting. And the clear traces of precipitation was observed, especially in reaction with the DI water, which was expected. The carbonate will react faster with the DI water, and also clay will react more. So the precipitant, we looked at the composition of the precipitates on the pores. They contain oxygen, silica, aluminum, and potassium, and also they are deficient of magnesium and iron. So they could be some amorphous silica, or they could be some combination of clay. So, but what we are suspicious about is the silica that is actually generated, and the amount of the amount of the dissolution was so high that in 10 days we observed that huge amount of precipitation on the surface of the rock. And we use various imaging techniques, from confocal microscopy to SEM with EDS, and also we conducted NMR analysis. I did not include it here because of the time limitation, and we analyzed the composition changes in basalt surfaces during the hydrothermal reaction. These techniques actually helped us to understand the mineralogical transformation on basalt surfaces. So, and the next would be to understand what we are producing. And in terms of the dissolution, we actually, a colleague of mine checked the composition of the water that we produce in the effluent, and we observed that the concentration of calcium, sodium, and potassium in the effluent increased by few folds, and in a very short period of time, as small as like few days. So with that, thank you so much for listening to me. I would like to thank my advisor and my colleagues at ESCM group at Harvard, and also ARPAI and SLB for funding this project. Thank you so much, and I'm sorry for the difficulties, technical difficulties that happened at the beginning, and I would be happy to answer any questions.
Yeah, thank you very much, Negar. Do you hear us? I assume Negar still cannot hear us. Can you confirm that you can hear us, Negar?
Okay.
All right.
Hear us, Negar.
Okay. Yes, I do hear you.
Okay, great. Thank you very much for the talk.
Hear us, Negar.
But I also can hear back myself, so if you can like reduce the volume, that would be great. There is no question in the comments, so for the people online, if you have any questions, please go ahead and type it down. I'm gonna read it to you. But meanwhile, I have a question. Can you please like comment on how do you sample actually from the water or vapor that you have in your chamber? Because I assume like if you let your chamber to cool down, the sample that you get wouldn't have the same properties while it is still under the pressure and temperature.
Yes. We checked the sample actually both immediately after after opening it, like we took it out of the oven, and when we opened it immediately, took the sample and tested them. All of those dendritic structures happened over there, but also we checked it after 2 weeks. The composition and everything did not change. The only difference that we saw were those dendritic structures on the surface of the sample. I do not have an explanation for that. Maybe there are some like reaction that happens in the surface, but yeah, I cannot confirm.
Yeah, sure. So to be sure, like you sample from the liquid while the pressure reduced to atmospheric pressure, then?
Yes.
Okay. Do you think that this sample would represent like the actual liquid, like in the reservoir, because there, like the pressure is gonna remain, at the reservoir pressure all the time? So I assume the deposition that you're gonna have over your sample, like either solid or maybe some dissolutions in your liquid, would be different.
Yeah, that's a good point, actually. That's why the next phase of our sample would be to conduct these experiments under dynamic condition. The dynamic condition meaning that while we are conducting the experiments, we can take sample and we can measure pH, like while the experiment is running. About the samples being under pressure or not, or ambient condition, unfortunately, we cannot conduct any ICP analysis on the the sample that is under pressure, or the liquid that is under pressure. But one good thing would be to use this sample in the NMR. So, and we can look at like what changes happens in the NMR during the reaction, or right immediately when we take them. That may help us understand something, but you're right. Yes, exposing the sample to the atmosphere and to the like the room condition, even that may change some of the stuff. But one thing that we did is just to take the sample immediately after opening, and also check it right after opening the chamber, and also check it in 2 weeks. We did not see a lot of differences in the composition of the minerals. Whatever was literally was just negligible.
Okay.
So, yeah.
Thank you very much. Do people at the studio, do you have any questions?
I have one question. It's
Yeah, go
actually,
ahead.
it can be a dumb question because I don't know much about this topic, but I was curious, after the incubation, there was an increase in the pH. So can you explain a little bit about the chemistry that's going on and what caused this increase in the pH?
Yeah. So when we put the sample inside the water, the hot water reacts with the surface of the sample. We are releasing a lot of the primary minerals like magnesium, iron, sulfides, and stuff. All of those elements, when they are added to the water, they contribute to our like increasing the pH. And at the same time, when the pH increases, initially we are not only dissolving those kind of minerals, we also dissolve like any composition of the carbonates, clay, or whatever that exists on the surface. So, and the carbonates, clay, and stuff, they are going to start to precipitate in the alkaline condition. So the primary mineral, which is like iron, magnesium, and the first group, titanium, they stay in the solution, while the secondary mineral, that are like any combination of the carbonates, silica, or clay, they are going to start to precipitate in the basic condition. So that's where it comes from.
Thank you. And can you explain a little bit about the dendritic structure you found? You said the structure disappeared after 2 weeks?
Yes.
So did you left it in the dried environment, or did you keep it in also the chamber for 2 weeks?
Both. Yeah, we tried both. So initially, when we saw that, we thought it's normal. So, and we took it out, we checked it, and then after 2 weeks, we wanted to get like another, like the tile scan of the entire surface, but we didn't see anything. So in the next experiment, we let it stay there in the water for 2 weeks, for until it cools down, and it was just 1 day actually. So when it was dry, we checked it after 2 weeks, but I'm not sure when it disappeared because we didn't check it any time in between. But when we left it in the water to cool down, we checked it the next day, and we couldn't see anything while the water like cooled down. So, and everything was just normal structures that we could see. We are still working on that. So, and it's definitely something interesting, but yeah, that one is just undergoing research now.
Wow. Yeah, thank you. I think it will be interesting to find out what is actually going on, but I look forward to see your next findings.
Thank you.
Yeah.
Okay, thank you very much, Negar again. Yeah, we moved to, actually, we have for the next session of the Porous Media Tea Time talk, we have 2 excellent talks here. Book the dates, and we're gonna see you here, hopefully, on behalf of the Porous Media Tea Time Talk organizers. I really thank people for following us and watching the videos, and we hope to see you at our next sessions. Yeah, thank you very much. Bye.